The expectation is that I tell you about my problems. There are no problems. At best, there are challenges or opportunities. So, and we'll talk about, and also the question is, you know, we are in good times relative to data. Big data is here, despite all the past. Big data is here. And so also, as you all know, we have big platform for processing and for storage. And now we have predictive analytics, predictive modeling in order today to take advantage of this. And those models are now becoming very essential in many fields: education, business, government. In fact, it's so much so that the field of data science, which is at the center of it, was dubbed the sexiest profession for the 21st century, or something to that extent. So exciting. So let's go and see what it's all about. So from 10,000 feet altitude, data science predictive modeling is pretty straightforward. The focus is on algorithm design, on optimization, on model building, and those are in the golden blocks of this diagram. And all the glory is go to this part. On the side, of course, there are some other supporting stuff that get very little attention, not mentioned very much, you know, the supporting things. However, it was observed that a data scientist spend less than 20% of the time on building models or doing the modeling, and 80% on what? So what we would like to see is, what are these 80% and why? And in order to do that, let's take a closer look, which is a little bit more complex. Turns out that predictive modeling and big data have gap. Because predictive models and machine learning and artificial intelligence, all of these kind of nice words, they like data that is well organized, known in R as data frame. You want the data to be well understood, well organized, and statistically well behaved. On the other hand, big data is observational mostly, is distributed among multiple sources. It is sparse. It is partially unknown, partially unreliable, and sometimes it is even irrelevant. And so in order to go from A to B, to bring the big data to predictive modeling, you have to take a few steps that my center argument will be that they are critical and they are the one who makes the difference. And I partition them quite arbitrarily into 3 steps. The first step is data exploration, when you actually go and explore the data. Then you go into doing something about what you found out in the data, known as data munging. And after that, when you have a coherent data set, you go and reshape the data in order to make it consumed better by the model. And after that, before you run the data, you have run the model, you have to do model tuning, and after that, of course, you have to go and evaluate the results, etc. And people will argue, yeah, but this was done for a long time. A lot of people did that, even for small data. The point is that the sheer magnitude, the depth, and the width, and the structure of big data makes a qualitative difference in it, and therefore it forces process adjustment. You have to think and to do things sometimes in a new way, and you have many decisions to make, and you have to know a lot of things in doing that. So let's go about this briefly, because this is a short talk, about in data exploration. First of all, you have to understand the data, what's in the data. Sometimes, at least what I'm doing, I take data, I have no idea what's in there. You have to figure out what's in the data. For example, you want to see what are the distributions of that. You have a lot of null value. This means sparse. And in data, for example, you get null values, the different input, put them in different symbols. Do you know all of them? You don't put that, the model will think those are actual values. So you have to unify them. Sometimes text, what language is there? You have multiple sources. Do you have the joint key in order to actually join the pieces into one thing? What are the correlations between them? And of course, sometimes you have to visualize, and visualizing you need to do with millions of dots. This one has a few hundred thousands of dots in it. You have to do special adjustment to the visualization on the screen, otherwise you get a blob. So those are different things that you need to do, and the objective here is to take this mess known as big data and create one unified data set. When you have the unified data set, now you have to go and do something about your observations. And you see there, you see categorical values, you see irrelevant or redundant value, you see missing value, you see a lot of things, and you start to make decisions about them, because this data managing, in my definition, is you have to go and transform each and every feature, each and every column in the data. For example, in the categorical value, you leave them alone, or you want to make a lot of dummy variables, or you would like to group them into subgroups. You have missing values. You want to just unify their symbols, or you want to discard them, or you want to impute them. Similar things, for example, if you have a skew distribution, what kind of transformation you want to do? And there are quite a few of those, and the point here is, in order to make all of these decisions, the data scientist must know both methods, the impact of those transformations on the model, and how the algorithm will actually take them. There is a lot of trial and error, a lot of experience. You need to know your tools. For example, R, the language R, people know it, offers for each one of these functions multiple functions. One of the challenges is which one of those functions you want to use in order to take the best performance, the best results for your big data column. One very simple thing, for example, if you work with Unicode, sometimes you write it to disk and you want to read it, all of a sudden you get messed up data set. There are different functions that will read data set that are a little messed up with 10x different in speed, and some of them will fail. And we won't name names right now, but those are the things. And so, okay, now that you have the nice Munch data set, you have to do feature engineering, and the objective is to look at the whole data set and to reshape the data set in order to bring it to better represent the underlying problem to the model. And there you can do it basically manually. We talked about dummy variables, but also if the data is not very well balanced, you want to balance the data. And to balance the data, you need to be oversampling or subsampling. And then you want to do part of dimensionality reductions by algorithm, let's say by PCA, or by matrix factorization, or by autoencoder, if you like the fancy stuff. And some of those dimensionality reductions even built in the model. For example, we see here lasso, which is L1, L1 regularization, and L2 regularization. Those are built in the models and will come built in the model, but you have to put them in. And the point there is that this is very critical because better features will allow you to work with simpler models and better results. If you want to push this even further, I would say that this type of extra steps sometimes make the design of the algorithm, the selection of the model, much simpler. So this is very critical. And so now you got that, and you want to put it into the model. Before that, you have to tune the model. The modern algorithms for modeling, et cetera, machine learning, have a lot of parameters. So you have to select which parameters to use in the model. For example, what is the learning rate? You want to learn fast, and you want to go slow in the optimization, go very fast optimization, and maybe miss the minima. And sometimes you have to take multiple parameters and work with the model on all the combination, all the parameter grid. You have to decide how many of those you take because they grow exponentially. And every one of the parameter grid requires a full run of the model, so it takes a long time to do that, so you have to use the judgment. A lot of trade-offs here, and also, of course, the ensemble. When you work with ensemble, you have to select what is the size of the ensemble, what is the level of the ensemble, and it is very well known. I don't know if you know the story about Netflix, the model, the ensemble model that got the $1 million, they never used it because it's too complex to do scoring later. And so now you have the model tune and you run it, and after that, after the model run and gave you the results, you need to evaluate it. But here is the point. If you go the textbook evaluation, you know, average or false positive, false negative, and things of that sort, what you have to listen as a data scientist to what the business is, because business will consider differently false positive versus false negative. For example, if you try to find fraud, false positive may cost you in public relation. False negative will cost you money. How you evaluate the two. And when the model runs in the field, you have to continue to do it continuously, following to see what the results in actual operation in order to improve the model. Now, we've talked about a lot of steps, and you would like to use the steps on one coherent platform, and there are quite a few of those. And I would like to mention one, the only one that I mentioned by name, is H2O, which is an open source Java machine learning platform that I worked with for like about 1.5 years. And they also offer some good facilities for data managing. And, and they can auto-detect. And in fact, they offer also R API and Python API, so you can run R, which I do, or run Python. The thing is, they also even give you, and my mantra is real men use command line, but they offer GUI, graphical user interface. And the good news, very sophisticated, the good news is that someone who doesn't know anything about modeling can go to the graphical user interface and build a very sophisticated predictive model. The bad news is someone who doesn't know anything about modeling can go to the graphical user interface and build a sophisticated model. And so this H2O is also distributed, run in a cloud, run on Spark, which is the new shiny object nowadays. And so let me just summarize and say the extra steps that get the little publicity and the little attention make a whole lot difference and make that difference. And this is a very detailed-oriented, it's not just grunt work, it's detail-oriented that have a lot of impact on the results. This is the critical factor, knowing the details and knowing the models, the algorithms, the tools, the platforms. You have to make a lot of decisions. Each and every one of these steps require a decision, and the decision will affect how your model will work eventually. And you have to know your platform, and you have to do the performance. You have to do a lot of trade-off between model complexity and performance and time to complete. And if you do it all, then you get your prediction, if you do it right. Even with simpler model, if you don't do it right, then unfortunately you may get very long delays, models that run a lot of time. Some of them will break, will not complete. And the worst of all, they will complete, but will give you irrelevant results. And so this, just to summarize, this kind of neglected 80% should get a little bit more attention because those are the details that actually make the predictive model run. Not just, but they have a very critical role in that. Thank you.
I think it's time for 1 or 2 clarification questions. I have one.
Please.
So what was the most irrelevant model, or useless model you produced at PayPal? And what can we learn from that?
Is there another question here?
Okay, I have another question for you. But I will keep that for the panel. So let's first see if there is any other clarification question required. H2O is water. No. Yes, so nothing? Well, then actually, okay, please stand up, your name.
I'm Madhusee, I'm a grad student. And my question is, how important is interactivity in the machine learning pipeline, particularly when you're testing models, testing features, or what is a reasonable latency that data scientists expect?
The question is, how important is the interactivity in building model? Very important. Extremely important. Because of all of this iteration of trial and error, whenever you say, let's try something, you would like to get the results without having time to get coffee. And in a lot of them, and this is also one of those, especially when you go to big data, every run, which include optimization, maybe like a boosted tree, gradient boosted tree, can take a long time to run. So the faster it runs, the better it is. This is why I kind of mentioned the H2O that runs on a cluster, that run much faster, and I measured the run. I compared it to standard R and 10x faster speed in big data GBM, and also 10x in pulling big data from disk to memory. It's all run in memory, all the mantras in memory, etc.
Thank you. Well, of course, he has a deep pocket, so he can pay for all that cloud services. And a student is always bound with a little budget of the funds. So let's use your brains and outbeat the money power there. You, please. Oh, there's the mic coming.
Test.
1, 2, 3. Hi, my name is Raj Sen from MemSQL. I had a question on slide 2. You had the picture of Teradata and Hadoop. So in this pipeline, do you have any data that's in relational form in Teradata engine?
The initial,
do you have any data that sits in relational form in the Teradata engine, or most of the data is only Hadoop?
Both. I meant it. I mean, everything that no, he meant the next one. The next who? Yeah, this one. Yes, in the environment that I work with, we have Teradata, we have other RDBMS, we have Hadoop. Both of those are very large, but we are also using data out there in the wild, so the cloud, everything public data is also included in there. And it's by no means I wanted to go and preach for something to sell any of these products. There are enough people here to sell you the products. But what I meant is, as an example, that you can take the data from multiple sources, and something I didn't stress is basically you have to deal with how you put them, where you move them. The data movement is a whole thing, deserves a whole talk, which I didn't touch right now.
And as a follow-up, so are they separate pipelines, or you need to merge the results from the relational side and the non-relational side from Hadoop to get to your final model?
At one point, as it's shown on the next slide, at one point, you want, when you give it to a predictive model, you want to bring it to one coherent, let's say if you know R, this is data frame. Okay, you have a rectangular data set, whatever. So if someone will come and show how you can have this rectangular, a predictive model will go and take some of it. Somewhere it needs to be unified in order so that every row is a data point and every column is a feature. This is how the models work.